Welcome everyone. In this video, I'm going to talk about deobfuscation with revenge. Deobfuscation is a pretty hot topic lately. We've been in contact with many people using revenge for deobfuscation purposes, or that are willing to do so. So in this video, I want to give a brief overview of a few cases where you can use revenge and LLVM effectively to deobfuscate binaries. I'm going to start with a quick introduction to set the scene, and then I'm going to move on with 3 different examples with increasing complexity of different compiler-based obfuscation techniques that can be tackled with revenge today. I will close with the next steps with an outlook on what you can do with the output generated by revenge on obfuscated binaries. So, obfuscation, first of all, it's an arms race. There's a very broad spectrum of different techniques and countermeasures that are always improving and always moving. So clearly, revenge is not a universal deobfuscator. It doesn't aim to be. In fact, I think that the very concept of a universal deobfuscator doesn't make any sense because of the very fact that obfuscation and deobfuscation is just a moving target. So what this video is about instead is the fact that the revenge is a very good place to be if you're trying to do deobfuscation of a specific class of obfuscation techniques. These techniques is what I call compiler-based obfuscations. They are techniques that are typically applied by a compiler, but they don't necessarily need to be. So they are techniques where the obfuscator reasons about the structure of the program, typically expressed with the intermediate representation of the compiler, but not necessarily, and apply transformation that a compiler could apply to make the program harder to reason about. And when I say compiler-based, I wanted to contrast it explicitly with VM-based obfuscation, which is an entirely different class of techniques where the binary being obfuscated is basically retargeted at a different architecture, which might not even be an actual architecture, but it could be a virtual machine. Okay, there's plenty of these approaches. They're out of scope for today, and as well as other approaches that are not compiler-like, so that are not amenable to be implemented as part of a compiler. Also, of the approaches I'm going to show today, there might be more complicated version, different flavors. I don't necessarily claim to cover every possible approach, but this is just a starting point to show what is possible to do with revenge and the building blocks that we can use to build more complicated pipelines for deobfuscation or for handling more complicated cases. So, like I said, I'm going to do this on 3 different examples. Before jumping straight into it, I want to stress that everything you're going to see today live is available on a demo GitHub repository. You can check it out, you can clone it, you can run it in Podman or in Docker for maximum reproducibility. So go ahead and do it, and if you have problems, report us, and we're going to try and help. Let's get to the first example. The first approach I'm going to talk about is code mutation with stack traffic. Code mutation is an obfuscation approach where the obfuscator considers a single instruction at a time, possibly a small chunks of consecutive instructions, and rewrites them in a way that replaces them with different instructions with the same equivalent semantic, but that are harder to reason about for tools and analysts. An example of this is when the obfuscator injects lots of back and forth traffic from register to the stack frame and back. In this way, intermediate results of computation that was already obfuscated with mutation goes through memory and forces analysts to reason about aliasing and about how values propagate across memory, which is notoriously harder. So let's start with an example. We have a simple function in x86 assembly. It takes a single argument in the RDI register and it adds 42. The result is put in the arrayx register that is also the return register. This is a very simple function. And if you feed this into an obfuscator, into a mutation engine, let's say, that does code mutation and adds and injects useless stack traffic, what you might get out of it is the following obfuscated sample. So the single argument of the function is again taken in the RDI register, but this register is straight away pushed on the stack. Then the value is copied back from the stack into the RDX register. And the RDX register is where all the magic happens, because the next three instructions are three XORs with weird magic masks. And the gimmick here is that the three magic masks cancel out if you XOR them together, which means that at the end of execution of line 6 in RDX, you have the same value that was passed as argument to the function via the RDI register, except that now you have it in RDX. So RDX is put back on the stack, and on the stack, the value is incremented by 42. Finally, the incremented value is popped back from the stack into RAX register for returning it. So the obfuscated function has the same semantic as the original one, but is much more complicated to reason about. Let's see what we can do with revenge on this. This is our first live demo. Remember, you can see this on GitHub and try it yourself if you want. We have a small binary, sum42, -d. This contains a single function at address 404D8, which is the same function that I just showed you on the slide. It's just a little bit more verbose because I had to edit it to make it fit the slide, but the function is the same. So what we're going to do now is to analyze this binary with revenge. And we're going to do this with the revenge artifact command. This is how you can request revenge to extract artifacts from binary programs. So in this case, we are requesting the enforce ABI artifact from the sum42 binary, and we are asking revenge to analyze the program. So analyzing the program means that revenge, in order to produce the artifact you requested, performs a set of analysis that it deems beneficial for the first time it looks at a binary. And then it uses the results to generate the enforce ABI artifact. The enforce ABI artifact is an LLVMIR module containing a representation of your binary program. Due to how the revenge decompilation pipeline is structured, what you can expect to find in the enforce ABI artifact is basically what follows. Revenge has identified in the binary program the boundaries of the functions. It has transformed them into actually separate functions in LLVM. And it has detected ABIs and enforced that on the LLVMIR so that the prototype of the function in LLVMIR looks like the ABI says, okay? So in particular, this means that revenge in this artifact is able to recover all the register arguments and return values of a function, and those appear as explicit argument and return values of LLVM function in the module we are getting out. So this generates an LLVMIR module. We are piping it through a prettifier that I wrote for this demo and putting the result into the enforced.ll file. Okay, so this runs revenge, as I said. Now we can open the result in an editor. I'm using VS Code. Here it is. So as you can see, we have a function at address 448, which is the same we had in the original binary. It takes a single argument and it returns an integer. But besides that, everything else is a little bit sad. There's still lots of references to RSP. There's lots of traffic back and forth from the stack frame pointed to by RSP. There's the three XORs are still there. So at this point of the compilation pipeline, Revenge wasn't able to understand what they do. And then down here, drowned in all the stack traffic referred to RSP, you can find the add 42. And if you track this down through memory, you're going to figure out that their value is returned by the function. So add 42 is actually returned to the function. But this is not very, very helpful if you're trying to look at the obfuscated code. But don't worry, this is just one of the artifacts you generate with Revenge. And in fact, you might have noticed that among the things that Revenge does in Enforced ABI, I haven't mentioned anything concerning the stack frame. So what we really want to do is to request a different artifact, in this case, cleanup IR. Cleanup IR is an artifact that Revenge generates much downstream in the decompilation pipeline. So downstream in the decompilation pipeline means that it is at a stage where the Revenge decompilation pipeline was able to recover much more information about the high-level structure of the code. In particular, it was able to detect the size of the stack frame. And in the LLVM IR representation of the program that Revenge deals with, the stack frame was effectively promoted to a local variable in an LLVM. And the very moment you do that, you are unlocking LLVM to do local analysis on the stack frame, on the variable represented in the stack frame. And this effectively enables LLVM optimizations that run as part of the Revenge decompilation pipeline to split the stack frame up into scalar values and to propagate constants and through them, okay? With the result that LLVM analyses are able to figure out that the three XOR masks cancel out and that the stack accesses are not necessary, okay? So if we run this without running anything else, we can generate the clean.ll output. And if we open this in VS Code, we are going to see that this is much better. Ta-da! So the function is the same, at the same address, 448, but now there's no stack traffic, there's no XORs, it just takes a single argument. That argument is incremented by 42, and the result of the addition is returned. So pretty cool, huh? This means that Revenge is able to lift obfuscated code, and as part of its regular decompilation pipeline, without having anything specific that is targeted at undoing mutation and useless stack traffic, Revenge is able basically to deobfuscate the most trivial cases of such techniques. Of course, you can build something more complicated that Revenge doesn't support out of the box, but this is already pretty impressive considering that we are not doing anything specific to counter obfuscation in this case, okay? And that's just a start, because we're going to see later that the LLVM IR you get out of the Revenge decompilation pipeline, lifted pipeline, can be used with other LLVM tools in case Revenge isn't able to deobfuscate out of the box some of the things that are making your binary complicated to reason about. So let's move on to something more complicated. Up to now, we have seen approaches that only deal with a single instruction at any given time, but they don't affect control flow at all. Control flow is plain, is not affected by neither code mutation nor stack traffic, okay? So there's a whole bunch of different techniques that are aimed at making control flow harder to reason about. One of these is control flow flattening. And what control flow flattening does is basically to turn every single function, the body of every single function, into a finite state machine. Now, this may seem very complicated, but I'm going to show it on a very simple example right now so that we can later see a more complicated example with Revenge. In practice, control flow flattening works in two stages. The first stage takes a function and it adds a new local variable. Okay, sorry. So this is a very simple function, and it only has an argument, and depending on the value of the argument, it performs some computation, do something, or some other computation, so do something else. And it always puts the result of the computation into a local variable that is then returned, okay? Now, this is very easy. And to explain how CFG flattening works, I'm gonna do it in stages on this example, with the hope that you can imagine the generalized, more complicated version. So the first stage is to inject a new local variable, in this case called the next, and this local variable represents the block that is supposed to be executed next at some given point of the program, okay? So after injecting this local variable, control flow flattening goes in every code block in your program, and at the end of it, computes what's the actual next block that should be executed when you're done executing the current block, okay? So in this case, in the init block, next is assigned to then or else depending on the argument, because depending on the argument, you might end up executing the then block or the else block. And then at the end of the then block and of the else block, in both cases, you assign next to return, because in both cases, you want execution to fall down here to the return block, okay? So until now, you're only injecting a new local variable and new computations to update it, to compute it in relevant places in the program. And control flow is not affected yet. The second stage is what heavily affects control flow. Basically, all the direct branches here in this function are replaced with a dispatcher that dispatches execution at the end of a block to the next block using the next local variable that you have just computed, right? So what happens here is that whenever you call do stuff, you initialize this to init, so this causes the first time you hit the dispatcher to execute the init block. Here you are computing the next, that might be then or else depending on the argument, and then you go back to the dispatcher here, so that the next time you hit the switch, depending on what is the value that was assigned to next here, you either go to the then block or to the else block. And in both cases, the then and the else block, they do their own computation, and they both set the next to return, so that when you go to the dispatcher, you hit the switch again, and the execution is properly dispatched to the return block, okay? So this is, in a nutshell, what control flow flattening does. It's one flavor, a very simple flavor. There might be others, but you get the idea. So if you want to figure out, if you want to see this in another way, you can look at how the control flow graph looks like. The original is a pretty simple diamond-shaped if, then else, with the return block down here. And when you flatten it, you end up with the dispatcher, and each block goes back to the dispatcher itself after setting the next variable. This is already pretty ugly, even if the input was very simple. Imagine what happens with non-trivial cases. And non-trivial cases is what we are going to look at now, okay? So let's move on to the next example. We have an executable file this time, which is bigger. So this is a statically linked calculator in reverse Polish notation. This includes the whole libc, so it's not huge, it's not Chromium or GCC, but it's still not a small binary, right? And what we're going to do now is to take a function from this binary and see how we can first obfuscate it and then deobfuscate it, okay? So first of all, let's take the function we are interested in out of this, okay? And we are doing this again with the revenge artifact, clean up IR from the calc binary this time, and again analyze it. Then we are piping it to the pretty CFG prettifier. It's not doing anything fancy, it's just clearing up the LLVM IR so we can look at it better. And we put the result into the original .ll. Now, the original .ll is not obfuscated, okay? It's not flattened. And the reason why I didn't take an obfuscated malware sample from the wild is that real-world obfuscated programs apply many different obfuscation techniques at the same time, and I wanted to have a synthetic case where we can only see the effects of CFG flattening and deal with it, okay? So we have this program, we have the original LL, that is the non-obfuscated code we are gonna start from, okay? So let's take a look at the control flow graph of this thing. We are doing it with a OPT, which is an LLVM tool, with the view CFG only pass, which is going to show us a graph of the control flow graph of the function we are interested in. There we are. This is our control flow graph. As you can see, it's not trivial. It's not ugly, but it's definitely not trivial. There are two loops, a small one in here and a larger one induced by this big back edge. And there are switches, so, and the larger and the smaller loops are nested, so it's doing something not obvious at first sight, okay? And this is still the non-obfuscated version. So what we're gonna do now is to take this and obfuscate it with a CFG flattening pass I wrote myself in LLVM, so that I can later show you how we can undo the CFG flattening using LLVM tools. Let's get to it. So I have an analysis here. It's the CFG flattening pass I wrote. It's like 100 lines of code. And what I'm doing now is I'm running again OPT, which is basically the optimizer of the LLVM framework. And this time I'm saying load the library that contains the pass I wrote. And I ask to flatten the CFG. And then there's some LLVM incantation to disable the new pass manager. This is not really relevant for today, but I need it to make it work. So the input is the original LN, and the output should go into, let's call it the flat.ll, okay? So this applies our CFG flattening on the original LLVM. Remember, this stage is usually performed by the obfuscation tool, okay? So the binaries, the obfuscated binaries you get are gonna look like the control flow we are gonna take a look in a moment, okay? So let's take a look at the control flow of the flat thing. Here it is. As you can see, it's a big switch. There's nothing you can figure out about the function just by looking at this. We can see some similarities. You can see that the switches that were present in the original function are still there, but the only reason why we are able to say something at all is that we knew how the original non-obfuscated version was. Imagine you are trying to analyze this and you don't know how the original code looks like. This is really ugly, okay? And this is how your obfuscated binary control flow might look like. Now, what we're setting out to do is to basically undo that. And the cool thing is that we can do this out of the box with vanilla LLVM tools without having to write a single line of code. And that can be done using a different LLVM pass, jump threading, with a special flag, jump threading across loop headers. Flat, unflat, let's call it. So what's happening here? What is jump threading? Jump threading is an LLVM pass that works on basic blocks with many predecessors and many successors. LLVM looks at all the predecessors and at all successors, and if it's able to figure out that when you come from a specific predecessor, you always go to a few specific successors, LLVM is going to duplicate the block you're looking at and inline it so that it is effectively able to disentangle different versions of the same blocks in different paths. And this, in this case, thanks to the other flag I passed, which is jump threading across loop headers, LLVM can do it on this big switch. And the end result is that the whole switch is completely unraveled and we can get the completely unobfuscated control flow outside. Let's take a look at that. On flat. Okay, remember that we are going to look now at the control flow graph that we got out thanks to jump threading from the flattened obfuscated version, okay? Here we are. And this is the obfuscated code that was effectively unobfuscated by LLVM. Let's compare it with the original. We have the original on the left and the unobfuscated on the right, even if control flow flattening did turn the original code into this huge switch mess, okay? Cool, pretty cool, I think. Basically, unflattening is free with LLVM. This is yet another demonstration that LLVM is a great toolbox. It contains lots of analysis and optimizations that you can use to build compilation and transformations flow to your specific ends, okay? And the cool thing is that Revenge, even if it doesn't support control flow unflattening out of the box, can generate high quality LLVM IR that is perfectly suitable for handling, for using with general LLVM based tools. So that's what enables us to play around with flattening and unflattening like I just showed you. So let's now move on our third example. The approaches we have seen up to now only deal with a single function at any given time. Now we're going to see a more advanced example of an approach that involves many different functions, okay? So one of these, of the very basic approaches that you can use to force the analyst to look around in many different functions is to inject opaque branch conditions, okay? And let's see how it works on a very simple example. Originally, your input program that is being obfuscated contains this very simple function that just adds 2 arguments. Pretty neat. The obfuscator can complicate this by adding lots of unreachable bogus code, okay? So it effectively injects a branch, a conditional branch that wasn't there, and in the else, it injects bogus code. In this case, it's a shift, but in practice, it can be arbitrarily complex code, including loops and complex control flow. The point is that if the analyst cannot tell that the branch, so the if condition is always true, they might end up analyzing code that is unnecessarily complicated, that is never executed in practice. Now, in this case, it's very easy to figure out that the S branch is dead code because all the operands of the condition are constant. And that's exactly what injection of opaque branch conditions does. So it takes the branch condition that is easy to figure out, that is always true, and it splices it up into a separate function that is now opaque. Okay, so now just looking at the body of this function, you can't say that this is dead code. In order to be able to do that, you have to look inside the body of obfuscated add42 and understand it for the specific arguments you are passing in here. Okay, so this is one way you can inject opaque branches when you obfuscate code. And this is the example we're going to work with to see how we can deal with it with Revenge and LLVM. Let's go on with a new example. So here we have a new binary, add or shift. It contains assembly code equivalent to the C code that I already showed you. So we have add or shift. It's calling obfuscated add 42, which is the opaque branch condition. If you look down here, there aren't any explicit branches because there is a conditional move that basically selects among the result of shift left or the return value of obfuscated add 42. But the important property still holds. So looking at add or shift, you can't really tell that part of the code in here is dead, is never going to be executed. Its results are always going to be discarded. So let's see what Revenge can do with this. Again, we lift it, we generate an artifact, Revenge artifact, cleanup IR, this time on the other shift binary, and again, -- analyze. Prettify the thing so that it doesn't look too ugly when you look at it. And we put this in the initial.ll. Running this, let's take a look in VS Code. Initial.ll. Here we are. So we have a function that is our add or shift function, and the other function, which is our obfuscated add 42. The LLVM-IR isn't too ugly. It's definitely shorter and more concise than the assembly, but you still have the select instruction that is selecting among the result of the shift here and the result and the return value of the call, okay? So, again, even if you look at this LLVM-IR and you don't understand what the other function does, you can't really tell that part of the code is dead, okay? But don't worry, we can work around on this. Again, the output generated by Revenge is regular LLVM-IR, so we can use regular LLVM tools on it. And in this case, the tools we have to use are very simple. Again, we can use OPT. OPT is the optimizer of the LLVM framework. We instruct it to execute the O2 optimization pipeline on the initial.ll file. And we pipe the output, we put the output into a final, let's call it final.ll, and look at what we get. This is final.ll, and it is now clear that our function takes two arguments, %0 and %1. It adds them and returns the result. This is due to the fact that the O2 optimization pipeline was able to do function inlining, so effectively the obfuscated, the external function was inlined in the call side, and then constant propagation was able to see through the add 42 and figure out that one of the branches was never taken. So again, success. Revenge cannot deobfuscate this out of the box, but it produced LLVM-IR that is very suitable for deobfuscation. So we have great off-the-shelf LLVM optimizations that you can use as building blocks and build your own dedicated pipelines for deobfuscation. And that's it. So we have seen three different examples. We have seen in various ways that Revenge, on the one hand, doesn't explicitly handle obfuscated code and as a separate use case, let's say, but it is built with LLVM tools. It generates high-quality LLVM-IR, so it might be able, in some cases, to already undo some of the simplest obfuscation techniques. And wherever it can't overcome them, it spits out LLVM-IR that you can use as input. And LLVM comes with a huge toolbox of cool analysis and transformations that you can do. Like code inlining, outlining, we have seen that code elimination, constant propagation, we have seen jump threading. I mean, there's many more of them that can be repurposed for deobfuscation. So what's next? You can take LLVM-IR generated by Revenge as a starting point. You can use LLVM to build your own deobfuscation pipeline. And in the cases where Revenge is already able to overcome obfuscation that is found in your binary, you can visualize the output of Revenge in our UI that is based on VS Code, and you can check out the decompiled code and possibly expect that it comes out deobfuscated if Revenge was able to see through the simplest obfuscation techniques. So that's it for today. Thank you for watching.